All right, in a moment, we're going to use that relationship to work some problems. But before we get there, the first thing I need to do is this perimeter problem. Letter B. In the given similar figures, the perimeter of the large hexagon is 120 feet. Determine the perimeter of the small hexagon. All right, so what is the scale factor between the large hexagon and the small hexagon? So in order to work this one out, so this is going to be letter B. Let's put this one over here. In letter B, I have a scale factor of 1.5x over x. Okay, it's 1.5x in the large hexagon to x in the small hexagon. Um, and let me just make sure. So this side, 1.5 to 1, is going to equal 120 feet, which is the perimeter of the large hexagon, to y, which will say the perimeter of the small hexagon is going to be some value y. And you'll see why I'm using y. And I could just do 6x if I wanted to. But we'll just say that y is the whole perimeter, okay? Now, what's going to happen? In this first one, this x is going to cancel. So my similarity ratio just actually becomes 1.5 to 1 because I had x over x. Now I'm going to multiply both sides by y. 1.5 times y equals 120. And now I'm going to divide both sides by 1.5. So this becomes y equals 120 over 1.5. This is a job for a calculator. 120 divided by 1.5 is 80. So that means that our perimeter for the first hexagon, the smaller hexagon, should be 80. Let's see if we did that right. It's technically 80 feet. Let's just make sure that we got the right perimeter, 80 feet. All right, now we didn't use a square scale factor in that one because we were just dealing with perimeter. Let's see what happens with letter C. The two parallelograms given have a similarity ratio of 2 to 5. Determine the ratio of their areas and the area of the larger parallelogram. Okay, so if their similarity ratio is 2 to 5, that means that I'm going to write it like any sane person in a math class would write a similarity ratio. Instead of 2 to 5, I'm going to put it 2 over 5. But we need to square that similarity ratio to get the ratio of their areas. It's going to be the similarity ratio squared. So actually, from the small with the smaller area on top and the larger on the bottom, the similarity ratio is going to be 4 over 25. Okay. And then determine the area of the larger parallelogram. Well, the way that this is going to work is I'm going to plug in the area of the smaller parallelogram first. That's just going to be the length of the base times the height. So 60 over the area of the larger parallelogram x equals the similarity ratio for areas, 4 over 25. Remember, that's just the square of the scale factor. Now I'm going to cross multiply. 60 times 25 divided by 4. Let me just make sure. So 4x equals 60 times 25. So let's go ahead and do 60 times 25 divided by 4. That means that the area of the larger one is 375. So x equals 375, and that's going to be centimeters squared. Let's make sure we did that correctly. So we should have 4 to 25 is our similarity ratio. We're going to write it as a fraction, and then 375 centimeters squared. Lastly, the kitchen on a floor plan shows a triangle from the sink to the refrigerator to the counter that has an area of 1.5 square feet. If the floor plan has a scale of 1 to 10, what will be the actual area of the triangle when the house is built? All right, so that means that we're going to use a similarity, let's see, an area similarity ratio of 1 over 10 squared, which is actually 1 over 100, okay? Then we're going to take the area of the original 1.5 square feet. And let's see, the way that I always write these out, because it always works best to actually write out the problem. So it's going to be 1.5 compares to the actual as 1 compares to 100. We're going to cross multiply and divide. So this is going to be x equals 1.5 times 100. The actual is going to be x equals 150 square feet. And let's make sure we got that right. 150 square feet. There it is. So that is how you work these problems. You need to square the similarity ratio or the scale factor, right? You need to square the scale factor and then use that to compare the two areas. Alternately, you could just find the new length and width of your figure and then just use that new length and width, multiply them to find the area. A couple of ways to do this, but now you know how to do it. You're ready for the problem set.